So the attraction between an electron and the nucleus, the electrons are negative, the nucleus is positive, there's an attraction. That's going to depend on the distance from the nucleus. It's also going to depend on the charge of the nucleus. So there's attraction between the nucleus and the electron, but the electron is going to be repelled by other electrons in the atom. And so we've got this balance of attraction and repulsion. So the repulsions cause the electron to have a reduced attraction to the nucleus. The attraction is not as strong as we expect it to be. And this is called shielding. The total amount of attraction that the electron feels is called the effective nuclear charge, or ZF, Z effective, for the electron. No pictures. Okay, gotta make my own picture. It's fine. So here we've got a nucleus, it's positive, and here the Bohr model is convenient. So there's 2 electrons in that level, and there's an electron out here. This electron is repelled by those electrons, even though it's attracted to this. This would be 3 positive, I guess. So because these are in the way, this electron experiences less attraction to the nucleus than it would if those were not in the way. Okay, so here's a really weird example. So, attractive model. Having more electrons here is like the model putting on more and more clothing, right? So if she's wearing a snowsuit and, a parka and she's got her face covered up and mittens and everything, she's not as attractive as if she was wearing a bikini, right? Because you can't even see her. Strip off a few layers, now she's in a jeans and a t-shirt. She's more attraction than when she was all bundled up. But not as much maybe as when she's in a bikini, right? So this is like clothing. I know, weird analogy, you'll remember it though. So this shields the electron from the attraction of the nucleus. And so it is not as attracted. The closer an electron is to the nucleus, the more attraction it experiences. And this kind of works with people too. If you see someone from way far away, you can't be as attracted to them as if you were up close. So the closer the electron is, the more attraction it experiences. So the outer electrons, remember, they are not going in big circles around the nucleus. They're in those weird balloon shapes, those wave functions that we saw, right? And so even though in general they are larger and in general they're farther from the nucleus, they can be close to the nucleus. And that's called penetration. When the electron's orbital allows it to get through to be closer to the nucleus than perhaps some of the other orbitals. And that's related to the radial distribution function. Oh, here's the picture of shielding. So here's our picture. There's a +3 nucleus, and we've got these 2 electrons. This electron is going to experience less charge on the nucleus, less attraction, because these guys are in the way. So on a very simplistic level, we can say that these 2 cancel out 2 of the plus charges here, and so this is experiencing a charge of about +1 on the nucleus. Here, this electron has been able to get inside, to penetrate inside this area, and now it can experience the full +3 charge. It's also more attractive because it's closer. If we look at the radial distribution, so here we have the 1s orbital, and here's the 2p orbital, and here's the 2s orbital. So the 2s orbital has this little region here, which is much closer to the nucleus. So the 2s orbital can penetrate in outside the 1s orbital area and have greater attraction to the nucleus. The 2p orbital has a little bit of penetration here, but not as much as the s. Because of this, the 2s orbital is lower in energy than the 2p orbitals. As you move away from the nucleus, the energy becomes higher, becomes less negative, coming up from under the water to the surface where elevation would be 0. So the 2s orbital is lower in energy than the 2p orbital. So 2s and 2p, not at the same energy level, they're not degenerate. When we get to the 4th and the 5th principal levels, then the effective penetration becomes really, really important. And so then the 4s orbital is even lower in energy than the 3d orbital. And it gets really messy. The energy separations between the different sets of orbitals become much smaller beyond 4s. And so the relative energy ordering can actually vary among different elements. We're not going to worry about that. I'll just tell you it can happen. So this is the general energy ordering of orbitals for multi-electron atoms. So here's 1s and 2s, and here's 2p. Remember, 2p, there are 3 different sublevels, just different 3 different orbitals within that sublevel. They have different orientations, but these are going to be degenerate with each other. But they are higher in energy than the 2s because the 2s can penetrate closer to the nucleus and so has a lower energy. Then we have 3s and 3p. We see the same effect where the s orbital is lower in energy than the p orbitals. And here's 3d, but things have gotten really messy up here, and 4s is actually lower in energy than 3d. And then there's 4p and 5s and 4d, and it becomes a big mess. I'll show you how you can figure it out, though. I have to talk about a couple more concepts. The Aufbau principle. This says that electrons will occupy orbitals in a way that minimizes the energy of the atom. So they're going to fill up the lowest energy orbitals first. Orbitals in the same level have the same energy. This is the filling order. You can memorize that, or I'll show you how you can get it off the periodic table. Orbitals can only hold up to 2 electrons, and those have to have opposite spins. And Hund's rule says that when you're filling degenerate orbitals, so 2p, there are 3 2p orbitals. When you're filling those, the electrons are going to fill them singly first. They're each going to take their own orbital with parallel spins, and then they'll pair up when they have to. Okay, so here is my analogy to help you make sense of all of this. This is the Quantum Hotel, a discount resort for electrons in Mrs. K's Chemistry Land. Chemistry Land is a happy place for me. It might not be for you. That's okay. So the Quantum Hotel, it's a little bit weird. The first floor has 1 room. The second floor has 2 rooms. The third floor has 3 rooms. The fourth floor has 4 rooms. So it's like an inverted pyramid. Wouldn't work in California with the earthquakes. Each of the floors in the hotel corresponds to a principal shell in quantum mechanics. So n equals 1, 2, 3, 4, etc. So on that first floor with 1 room, that room is called the S room. And the second floor with 2 rooms, it has S and P. The third floor has S, P, and D. The fourth floor has S, P, D, and F. So each room corresponds to a subshell. So that would be quantum number L. And within the rooms, there are beds, because this is a hotel, right? People come here to sleep. So each of the beds represents an orbital. An S room has 1 bed. P rooms have 3 beds. D rooms have 5 beds. F rooms have 7 beds. Don't ask me why. They just do. It's kind of a weird hotel. I'd like to find a hotel that had 7 beds in 1 room, because then I could just get one room for my whole family, and people who don't want to sleep together wouldn't have to sleep together. Nobody on the floor. So a person in the hotel corresponds to an electron, and money, again, corresponds to energy. So the rule at this hotel is you can only have 2 people per bed. You can't have 3 or 4. And the people must have opposite spins. So what does that mean? Well, I don't know why I think of electrons as being masculine. Do 2 guys that don't know each other like to share a hotel bed? Or even 2 guys that kind of know each other? No. Somebody's going to sleep on the floor or in the bathtub or something, right? Rather than... So you can't sleep on the floor or the bathtub. So if there's 2 guys in this room, they have to sleep in the same bed. So what they do is one person sleeps with his head by the headboard and the other person sleeps upside down, head to toe. They used to do this back in the good old days, like in the 1800s. And at Fort Snelling, they had these narrow bunks, and it was like stinking, freezing cold. And they slept 2 guys in a bed, and they fit better head to toe, and then they kept each other warm. Not unprecedented. Okay. So we can think of this order of filling, or order of orbitals, as being sort of a diagram of the hotel. So here's the first floor. There's 1 room. Here's the second floor. It's got 2 rooms, S and P. The P room has 3 beds. So each of these lines represents a bed. This one's a little higher than that one because the price of staying in that room is more. The electrons come in to stay here. Remember, this is a discount resort. So these people are money conscious. They're trying to get away with spending as little money as possible. So they're going to stay in the cheapest room if they can. But if that room's already full, then they'll have to go to a more expensive room. So let's imagine a bunch of electrons coming in from a day at the golf course or whatever they were doing, and now they're going to fill up the hotel. So the first electron comes in, and he wants the cheapest room possible, and he goes in and he goes to bed, and he's going to sleep right side up in the bed, because that's what everybody does, right? So he sleeps right side up. And then the next guy comes in, and he also wants the cheapest room. Well, there's already one person staying there. It's okay. It's cheaper. Well, he's not going to sleep, snuggled up next to this guy he doesn't even know. So he's going to sleep upside down. Next electron comes in. He wanted that room, but it's full. So he has to go to a more expensive room. Sleeps right side up. Fourth electron comes in. He's going to sleep upside down. Next electron comes in. He's got to go into this P room. He's probably going to just take the bed closest to the door. Sleep by himself right there. Next electron comes in. He's going to get put into this P room because now it's the cheapest room that's available. Is he going to sleep with this guy? No, not when there's 2 empty beds. He's going to go take his own bed. Hund's rule. They're going to fill orbitals singly with parallel spins before they pair up. Next electron comes in. Is he going to share with one of these guys? No. Is he going to go up here? No. That would be really expensive. So they're cheap, and they like their own beds, but they're willing to sleep with other people. So he comes in, and he's going to be in here. Now the next electron comes in. Well, cheapness wins. He's like, well, I guess I'll go into this room, but he's going to sleep upside down. And then the next one, and then this one will fill, and then you get the idea? So that's the third floor. Now the next electron that comes in is not going to stay in this room on the third floor because that one's more expensive than this one. Why? I don't know. It just is. So he's going to go into this room. And then this room will fill, and then that one, and then this one, and then that one. They're going to go the cheapest rooms first. The lowest energy subshells are going to fill first. Each orbital with 1 electron until there's 1 in each of those in the subshell, and then they'll pair up. Any questions? Does that make a little more sense than the other stuff? Can you imagine electrons doing this? Yeah. So when we talk about electron configurations, unless it says specifically that it's an excited state, we're referring to the ground state, the lowest energy configuration. Because, we've got our electrons in here in their lowest energy states, but maybe this guy was gambling and he won a bunch of money and he wants to splurge and sleep in this room because he got a bunch of money in. So he's going to go up there and spend one night up there, but now his money's gone, and so he's going to end up coming back down here. The number of electrons in a neutral atom is equal to its atomic number. Electrons with parallel spin, because you might wonder, well, how can you have two negatively charged electrons in the same orbital? Don't they repel each other? Yeah, there's this magic thing about that's wrong. It's not parallel spins. It's opposite spins. When they've got opposite spins, they minimize their repulsion. That's bad. And then this again is the number of electrons that can be in each of those categories. So an electron configuration is just a listing of the sublevels in the order of filling, and we're indicating the number of electrons as superscripts. This is a place where we do write the number 1. And you could think of this electron configuration as being the hotel clerk's shorthand of what rooms are occupied so that he doesn't send somebody to a room that's already full. So for krypton with 36 electrons, we could represent this as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. You got that? Yeah. So it's filling this up. We get 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, blah, blah, blah. It's filling up in those orders. Well, that gets a little tedious, writing all of those out. So we can use a noble gas shorthand. It's also called an inner electron configuration. What we can do is we can use the symbol of the previous noble gas in brackets to represent the inner electrons. So this is the electron configuration for krypton. This is the electron configuration for rubidium. It's got one more electron. This part right here is the same as krypton because it always fills in the same order, at least in this class. So instead of writing all of that out, we say, well, it's krypton with this added. It's just a lot shorter. You need to be able to do both. So the orbital diagrams, so each of these boxes would be like a bed. So here's on the first floor, there's one room and it has one bed. Second floor, there's 2 rooms. The first room has 1 bed. The second room has 3 beds. And so we indicate that these are all together in the same sublevel by putting the boxes touching. So there's the 3 beds. So for carbon with its 6 electrons, the electrons are going to go first one in here, and then that guy's going to pair up, and then one in here, and that guy's going to pair up. And then these guys are going to each take their own bed. Because they can. Who wouldn't? The electron configuration is just a shorter way of doing this without drawing boxes and arrows, which on a computer is really tedious. So we look at the 1s. Well, it's got 2. So 1s2. 2s has 2. And the 2p room has 2 electrons in it. So 2p2. So that's the relationship between orbital diagrams and electron configurations. We have to stop here sometime. Okay, this last slide, then we're stopped. Write the orbital diagram for argon. Determine the number of unpaired electrons. So orbital diagram, so we got some boxes, right? So on the first floor, there's one room. On the second floor, there are two rooms, S and P. The P room has 3 beds. Then we go up to the third floor. Third floor. Are we going? Okay, that's far enough. So argon, how many electrons does argon have? 18. Yep, 18. So what we're going to do is we're going to take our hotel here and we're going to fill up the beds. And we're going to count. So we got 1, 2, 3, 4, 5. This guy's going to take his own bed. 6, 7, but they're cheapskates, so now they're going to share. 8, 9, 10, 11, 12, 13, taking his own bed again. 14, 15, pairing up because they don't want to spend any more money. 16, 17, 18. You see how that works? How many unpaired electrons? None. Orbital diagrams will show you unpaired electrons. Electron configurations will not.